Hello, my name is AubreyLanham, and today I'm going to talk about my summer research internship at the University of Florida. But first, let me tell you a little bit about myself. I live in Columbus, Ohio, but currently I'm studying biomedical engineering at the University of Rochester in Rochester, New York. As I gear up for my senior year this fall, it's time to start preparing for the inevitable question, what's next? That question led me to the SURF program at the University of Florida, where I had the opportunity to explore the potential path of pursuing a PhD. SURF stands for Summer Undergraduate Research at Florida and is a 10-week paid program where students can engage in cutting-edge research with university faculty and graduate students in preparation for a PhD. This summer, I was assigned to the Soft Tissue Mechanics and Drug Delivery Laboratory, where I worked in close collaboration with Dr. Santi Norinant, my faculty advisor, Maida Lotfi, my graduate student mentor, and other members of the lab. My project involved measuring the alignment of soft tissue fibers and engineered tissue constructs, such as collagen hydrogels, using polarized Raman spectroscopy. In the United States, there are currently over 100,000 people on waiting lists for organ transplants, but the availability of suitable donors is scarce, with less than 20% of potential donor organs actually being recovered. Tissue engineering and regenerative medicine offer the transformative potential to rebuild diseased tissues and even produce organs for transplantation. One critical aspect of this research is understanding the alignment of structural proteins in tissues, as it directly correlates with the mechanical properties and functions of the engineered tissues. Our lab has been at the forefront of groundbreaking research, and we recently developed a technique to characterize tissue alignment using polarized Raman spectroscopy. This innovative method involves observing changes in Raman spectral intensity as we manually rotate the tissue sample with respect to the fixed angle of a polarizing filter. But first, what is polarized Raman spectroscopy and how does it work? Polarized Raman spectroscopy examines the scattering of polarized light to provide information about the molecular structure and orientation of a sample. With polarized light, the electric field oscillates in a specific direction, providing valuable insights into the alignment and orientation of molecules within the sample. Now, to evaluate the fiber alignment in a tissue sample using our technique, we first collect and normalize the polarized Raman spectra. Then we apply a master loading function tailored to the specific type of tissue we are working with. Next, we use principal component analysis to filter the data, highlighting the relevant chemical bonds in the spectra while disregarding irrelevant variation. This process generates a principal component score for the different polarization angles, which we can then fit with a sine function to produce an amplitude alignment metric. An increase in amplitude indicates a higher level of fiber alignment within the tissue. While engaged in this project, however, I encountered two critical issues. First, the manual rotation and angle alignment of the tissue sample is inefficient and prone to error. And second, once the sample is rotated, it's difficult to relocate our region of interest under the microscope. In our current setup for the spectral acquisition phase, we drew lines at 30-degree intervals and attached it to the microscope stage as shown. The sample, which is held in a petri dish, was elevated by a metal block that could be lined up with the drawings. To investigate the accuracy of this angle alignment technique, I modeled the regions of interest, or the areas where we want to analyze a sample, as vectors. I then estimated the experimental polarization angles between each sample rotation using MATLAB. The results were enlightening. The experimental polarization angles exhibited significant variations and inconsistencies from the expected angle measurements. So how can we address these issues? Recognizing the importance of accuracy and reliability in our findings, I designed a rotation device that facilitates fixed rotation of a tissue sample around a calibrated center of rotation. Supported by a MATLAB program, the device allows for automatic relocation of the region of interest on the microscope software. With this device, we anticipate a significant improvement in sample alignment precision, leading to reduced time between spectral acquisitions. Furthermore, I developed a MATLAB program that utilizes the microscope's built-in coordinate system to determine the general location of the region of interest on the tissue sample after rotation. First, we run a calibration program to calculate the coordinates of the device's center of rotation on the Raman microscope software. Once these coordinates are known, the MATLAB program can estimate the new relative position of the region of interest at any given polarization angle. In ongoing studies, we will continue to evaluate the accuracy of the polarization angles for the rotation device using the same vector analysis methods that provided the experimental errors of the original method. The SURF program has been a truly exciting and enriching experience, granting me the opportunity to explore new and diverse areas within the realm of biomedical engineering. It has also provided me with invaluable insights into what pursuing a PhD in biomedical engineering or a related field would be like. Thank you for joining me on this incredible journey through my summer research experience at the University of Florida. For more insights and updates about my research, feel free to connect with me on LinkedIn, and if you have any questions, don't hesitate to reach out. Until next time!